Good morning, this is Jeremy. It's Friday, March 28th. I'm on my balcony here in Toronto, and our city is in lockdown over the COVID-19 crisis. When you look in the streets, you can't see anyone. Anyways, in the background here, I have my buddy pole, vertical antenna. It's base loaded, and I'm using that to receive station CHU. Let's just take a closer look at the antenna. So there's the antenna there. And so we're going to go inside and we're going to look at the received signal levels, and we're going to do some calculations. I did the actual receive signal levels yesterday, so that's what we'll do.
Canada, dans universelle coordonnée. 11h, 1 minute, 13 hours, 3 minutes.
Okay, so we just heard the CHU received levels here yesterday, Thursday, March I guess it was 26th, and we saw that at 3.33 megahertz, which is a lower frequency, we had around, let's say, minus 90 dBm, fading occasionally to minus 100. At 7.85, you could barely hear the signal, so it was down in the noise, and at 14.670, we didn't hear anything. So those are the actual receive results. Before we look at the VOACAP program results, let's just take a look at a few diagrams here. I'd like to get a handle on what's the best case receive level I could have. Let's say the signal left the transmitter and arrived at the receiver. It refracts to the atmosphere, but let's assume that there's no attenuation in the atmosphere, which is not realistic. So in this particular signal here, or this particular figure here, what I'm showing is the maximum hop distance. In other words, there's my transmitter, and let's say the angle, the takeoff angle from the transmitter antenna is 0, so that would give me the longest distance. And here, this outer circle here is one of the ionospheric levels. Let's say it's either E or F1 or F2. In reality, the signal refracts, so it bends in the atmosphere, and it comes down to the receiver at C. We can define a virtual height, okay, and then we can consider this to be a plane triangle. So we leave A, go to P, the virtual reflection point, and come down to C. So this great circle arc distance, AC, is the maximum propagation distance for one hop, and AP plus PC, that's the actual propagation distance. So we can use a law of physics to determine, if I know what my transmit power is, I'm going to have so much attenuation going that distance. So that's basically the upper level. We'll never do any better than that. This virtual height here, P, depends on the actual level. So if we go down to this table here, there's our virtual reflection height. Let's say for the E layer goes from 90 to 150 kilometers. So we'll say the average is about 120. There's F1, it goes from 150 to 250 kilometers. So we can say the virtual height's about 200. And there, F2 goes from 250 to 400. So we'll say the virtual reflection height's about 325. So that gives us our maximum range. For one hop on E, you can go to about 2,500 kilometers. For F1, you can go to about 3,000 kilometers, and F2, you can go to about 4,000 kilometers. That's the propagation delay in milliseconds as well. Okay, now in this figure down here, what I'm doing is I'm saying, okay, let's say my hop from A to C is less than the absolute maximum. So then what's happening is the signal from the antenna is taking off at a takeoff angle alpha. And if we know AC and we know which layer we're dealing with, we can work out the takeoff angle alpha. The reason this is important is because antennas have a gain that varies with the vertical takeoff angle. So for instance, if I look at a program called EasyNet, EasyNet will give you the vertical radiation pattern of an antenna. So here I have a quarter wave vertical at 3.33 megahertz. So there I'm looking, let's say, at 34 degrees. So my gain is a 0.21 dB. Down here, it's this is at 48 degrees. It's minus about 2 dB. And there's 61 degrees. There's minus about 5 dB. So you can see, depending on the vertical angle, the gain of the antenna can be different. So here we have some basic physics formulas. There's the formula for the received signal power. So the received signal power over the transmit signal power depends on the two antenna gains and the radius separating, or the distance separating the two antennas, and that's the wavelength. We usually deal in dBm for received signal levels. 0 dBm is 1 milliwatt, so it's 10 log the number of milliwatts. So I can convert this formula to dBm. So this is a receive power in dBm. That's the transmit power in dBm. Those are the two antenna gains, the receiver and the transmitter. This is an adjustment factor. This is 20 log to the base 10 of f. This is the frequency in megahertz. And there we have 20 log of the distance between the antennas in terms of kilometers. So we're talking dBm, megahertz, and kilometers. Now, if we're just going to consider the free space loss, okay, so we can lump all these three terms together, and that will give us what we call our free space loss. In reality, though, this is not correct because there's going to be absorption in the atmosphere or the ionosphere, so we'll call that Li. And if there's more than one hop, you'll have reflection ground loss. So really, in a real situation, which is what VOACAP does, you have to consider all three. What I'm doing is I'm just looking at this to give me a maximum signal I could ever possibly receive. Now, if we look at the noise, of course, at the receive end, for decoding, we need to know what our signal-to-noise ratio is. So we need to know what our noise is. So our thermal noise is kT0b. That's the Boltzmann constant. But in practice, our noise is going to be a lot higher due to a whole bunch of different factors here. So here's a table from the ITU recommendation 372. And we've got to consider atmospheric noise, man-made noise, galactic noise. And in a city, of course, you've got all sorts of noise from various sources. So in other words, our thermal noise will be increased by a noise factor. So if we want the noise in dBm, we use this formula here. So the noise power in dBm will be this factor, the noise factor, plus 10 log. Now, this noise here is dBm per hertz, so we have to convert that to our bandwidth. If we're talking SSB, CHU transmission is upper sideband, so we're talking about 2400 hertz bandwidth, so we have to include that factor there to get the total noise. And again, we just read this particular table to get our FA. So down here, what I've done is I've just summarized the results of the CHU to VE3PKC. So in VOACAP, what you have to do is you have to put in the latitude and longitude. So let's just quickly do it. Go down to the VOACAP screen down here. There's the VOACAP screen. So on my transmitter here, I put in the latitude and longitude of CHU, which you can get from their website at the National Research Council. I put in the latitude and longitude for my location here. In terms of the mode, I've got SSB. The power I've set at 1,000 watts. Now the actual power of 3.33 megahertz is 3 kilowatts. So we have to make a 5 dB adjustment in the table. In terms of the antennas, the closest antennas are quarter wave vertical. So that's what I have on both ends. Okay, so let's go back to the table here. So I put in all those factors. Knowing the great circle distance, with Psychos Lab, I have in my ebook HF Telecommunications in Chapter 8, I give all the Psychos Lab routines to work out all these details. but I can calculate, as we've seen in previous videos, I can calculate my great circle distance between the two locations. That turns out to be about 339 kilometers. The bearing in Toronto is about 57.3 degrees, and the bearing at Ottawa is 240 degrees. So from those particular details, this is not the maximum one-hop distance. This is less than that. So we can determine our takeoff angles. So if I was to consider the E layer, the takeoff angle would be about 34 degrees. The F1 layer, the takeoff angle is 48 degrees. And the F2 layer, the takeoff angle is 61 degrees. Now here, what I've done is I've worked up their free space attenuations using the formula. I've plugged in 3.33 megahertz. Those are the actual propagation distances that we've determined over here. That gives us my free space attenuations. Here's my noise power. I'm using a noise figure of 58 for the 3.3 megahertz. So if I look at the table, the closest frequency is 5 megahertz, and the biggest noise would be, let's go to that table again. So 3.3 is closest to 5, and E is the biggest value down here. So that's typically what you see in a city, so that's 58 dB. So that's where that comes from. So I can determine my noise, and these are my received signal levels. Again, we're only talking about free space attenuation. We're not considering any absorption in the ionosphere, which is not realistic, but it just gives us an upper bound. Okay, so I take the power. The power is 3 kilowatts. That's 3 times 10 cubed watts, or 3 times 10 to the 6th milliwatts. So if I take 10 log of that, I get 64.8 dBm. Okay, now, so then I can work out 64.8. Now the two antenna gains, the antenna gain at 34.3 degrees is 0.2 dB. Okay, so then we have two of those, so that'll be 0.4. And then I subtract the free space attenuation. That's how I get my maximum receive level. And again, let's say at F2, the free space attenuation is 102.2 dB. The gain at 61.1 degrees is minus 2 point something, and if two of those, is minus 4.7, and two of those is minus 9.4. Okay, so that gives you my received signal levels. Now I didn't do it for the other, I didn't do the received signal level calculations for the other two frequencies because we didn't receive them. Okay, the actual receive level, if you look at the video before this, at 3.3 megahertz is around minus 90, fading down to minus 100. So that was taken on Thursday, March the 26th at 1300. Today is actually not the 28th, it's the 27th. Made a mistake outside. Now, if we look at the VOACAP results, we're going to see that at around 80 meters, which is close to 3.33 megahertz, our reliability is 97%. So let's go down here. That's my reliability graph that I get from VOACAP. So that blue line there is the 80 meter band, which is close to 3.3 megahertz. And let's look at 1300 UTC, which is like 9 in the morning. So you can see that's around 97%. Okay, so that's the reliability of the circuit. If you go down to the signal power probability distribution, let's look at 1300. So at 1300 hours, 97% reliability corresponds to a signal of minus 115 dBW. Now, minus 115 dBW. Now remember, our power is actually 3 kilowatts, so it's about 4.8 dB bigger than 1 kilowatt. So I have to adjust that minus 115. So let's say that's minus 110 dBW. And then to convert from dBW to dBm, I add 30 dB. So the actual VOACAP adjusted value here for 3 kilowatts, VOACAP saying our receive level should be around minus 80 dBm. Okay, and I saw around minus 90, so that's close. It's like 10 dB away, so that's not too bad. And of course, the other two signals at 7.85 and 14.67 were not received at all. So again, those are the antenna graphs. This is a propagation wheel. This gives you a quick look at all the bands. So for instance, if I go in here, the outer dial here is UTC. So if I go in here at 1300 UTC, you can see that the 80 meter band is somewhere between 90 and 100% reliable. The 60 meter band is, let's say, 70 to 80%. The 40 meter band is like 50 to 60%. So we did hear something on 7.85, but it was pretty weak. Okay, so that's just a summary, a little bit more detail, what we saw in the previous video where I just basically looked at the propagation wheel. Thank you.